Our example number 17 for our fourth topic here, my dear student, said that a sphere and a cylinder having the same mass and radius. We have two liquid body. The first one is the sphere and the second is the cylinder. Then both of these liquid body contain the same mass and also the same radius. They start from rest at the same point on an inclined plane. Both of these are starting from rest, starting from the stationary at the same point on the inclined plane. And they are released at row down at the plane. They are being released. Now assume that, my dear student, you have the inclined plane. Now you take those cylinder and also the sphere, release it together on the inclined plane to low down toward the bottom. So when they are low, now we are supposed to determine which one reach the bottom first. We are supposed to look which of those could reach at the bottom first. If they have the same mass, they have the same radius, and they are being released together, which a man of the following could have the great could reach at the surface firstly compared with the other. So figure number 4, a solution. As we see our solution here. Now we could consider only two examples. Now we are going to see two figures. Now the first figure will be our figure number 29, Roman A, and the second will be our figure 29 for Roman B. So this figure show how a cylinder and also a sphere at the top of an inclined plane low on an inclined plane. Kwa hii figure ndio inaonyesha namna ya yule sphere pamoja na cylinder anavyokuwa analong kwenye inclined plane. While this figure number 29 Roman B, this show the free body diagram. This indicated the free body diagram for each, including the force like gravity. This involve the free diagram that explaining about the forces that could act on that inclined plane. And those forces is like the gravity, also the normal forces and the friction. Kwa hiyo itajaribu kuonyesha hapo. As we try to see our figure 29 Roman A, this we have the cylinder and also we have the sphere. Each of these they are being allocated or placed at the same they are released at the same instant or at the same point. They try to rotate downward toward the bottom, as we try to see. But they form the angle theta, as we try to observe, my dear students. But on Roman A, on Roman B here, this is the figure that show the free body diagram of the forces. Free body diagram of the forces that could act on this rigid body, as we try to see. So the force that could act toward must be, it means the upward force must be equal to the normal reaction. This we have the downward force that could act on this rigid body could be equals to mg. And finally we have this angle theta. This angle theta that can could act on that boat. It means this angle theta must be equal to the angle that could be acted on that rigid boat. But the force on the inclined plane must be equal to mg sin theta. But this here could long by considering the linear acceleration, as we see A that represented the linear acceleration. We tried to dissolve this one, this free body diagram, and obtain this forces mg cos theta and also the mg sin theta. So using the same logic as in example number 16 for our fourth topic. Now let us apply the same logic that we tried to use on our example number 16 for our fourth topic. We could recall the dimensionless coefficient which is valid for every liquid body. For the sphere here, we could use the dimensionless coefficient equals to 5 to 2 divided by 5. But for that sphere, for that cylinder, will be equals C will be equals to 5 to 2 at 1 divided by 2. This is what we are supposed to use so as to solve this question. But after demonstrating those linear coefficient, now we were supposed to go and see our equation number 90 for our first topic, which say that question number 80, which will reach the bottom of this one. This is explaining how the sphere will reach at the bottoms. So the net force acting on the body as it is moved down to the inclined plane, difference between the two components is gravitational force. Kwa ile force net force ambayo itaakti kwenye kwa yule bot ambayo ana move, zile bot zako anapokuwa na move downward, atakuwa ni sawasawa na gravitational force ambayo ataakti along to the inclined plane, which is equal to mg sin theta. Here we are talking the downward forces. Hii force ambayo inakuwa inaziakti hizi ziweze kuslide roll on an inclined plane, itakuwa ni sawasawa na mg sin theta. So from the Newton law of motion, from the Newton's second law, we know that the force must be equal to the mg sin theta we minus by the friction. When we talk the applied force, we add by the friction force, we get equals to the forces that act along to the inclined plane, means mg sin theta. Kwa tukimake huyu force at the subject, utapata force ni sawasawa na mg sin theta minus the friction force, but this force must be equals to ma according to the Newton second law of motions. That will be our equation number 1. But each terms have their meaning. M represent the mass, G represent the acceleration due to gravity, and also this theta represent the angle from the along to the inclined plane and also to the horizontal of the inclined plane. So the force of friction F acting at that the point of contact provided at the torque about the center of the mass of the body. Kwa ile force of friction, the force of friction that active when the body is rolling on an inclined plane could provide the torque, my dear student, which is about the center of mass of the body. So the torque must be obtained by the formula, but it is formula kwamba torque ni sawa na force times radius, ambapo ni sawa pia na moment of inertia times the angular acceleration. This is how we can find. Now we are supposed to use this relation so to make a friction at the subject. To make friction at the subject, tutapata friction ni sawa na moment of inertia times the linear acceleration we divide by r. This will be the second equation. But for the first equation here, we are supposed to take the second equation and substitute into the first equation, so as to form our third equation, that is mg sin theta minus the moment of inertia times the angular acceleration we divide by r equals to ma. But this angular acceleration is equal to linear acceleration divided by r. Now let us go and substitute here. If we substitute, we get I divided by r square, as it is looked like here, my dear student. Now after this one, you take this value here because they have the same acceleration with that one. Press take it and go and put it into the right side. Tukipeleka upande wa kulia tutaenda kujumlisha. Mwisho wa siku tutafakti huyu tutakuja tutamfactor huyu acceleration at the subject so as to make it at the subject. Kwa tukishamfactor out alafu tukamake at the subject, tutapata formula acceleration sawa na mg sin theta divided by m, then we add by I divided by r square. So after this one, let us go and let us use this formula so as to get the linear acceleration for each liquid body. Now for the sphere here, because they have the same masses and radius, If we substitute C is equal to 2 divided by 5, now we could obtain that the linear acceleration of that rigged body of that sphere must be equal to 2 must be equal to 5 divided by 7 g sine theta. The same for the cylinder, it must be equal to 2 divided by 3 g sine theta. This is the formula that we can use here. So after this one, as we observe, is that since the sphere has the greater linear acceleration, if we make a comparison between the linear acceleration of that cylinder and that sphere, we observe that the solid sphere involve a higher linear acceleration compared with that cylinder. So it will arrive at the bottom fastly than that cylinder. So by saying that this will be at the end of our session here, now I would like to invite you again for another session. I wish you all the best. Have a nice moment.